Okay, so let's finish this problem. We just found, using long division, that our quartic polynomial here can be factored into x minus 3 and x plus 1, and then we got this new factor here, this x squared plus x minus 2. We got it by doing long division. So right now, what have we shown? Well, let me get my ink here. We've shown that our polynomial p of x is equal to our two factors, x minus 3 times times x plus 1 times our question mark that we just found, x squared plus x minus 2. So right now we are almost factored that all the way. We're going to talk about this last quadratic here in a second. But first let's see how we could have done this by using synthetic division. So this is based on, remember the 210 we had before. We said if it's 2 times 3 times some question mark. There are two ways we can do that. We could multiply the 2 times 3 to get 6 and divide by 6. Or you can divide by 2 first. So divide by 2. That cancels out. Then we'd have 105 equals 3 times our question mark. And so then we divide by 3. And we would get the 35 equals our question mark. So we can do the same thing here. If we divide first by x minus 3, and then we divide by x plus 1. Well, dividing by x minus 3, since it's a linear factor, we can use synthetic division. So remember how synthetic division works. We put 3 into the box, and we're going to list out the coefficients of our polynomial. So that's 1, negative 7, 1, and 6. Draw our line. The 1 comes straight down. Times 3 is 3, minus 1. So we add these, remember. So I'm doing negative 1 plus 3. So you'll hear me say sometimes 3 minus 1, because if I'm adding these, that's all I have to do. So it's just negative 1 plus 3, or 3 minus 1, which is 2. Times 3 is 6. Negative 7 and 6 are negative 1. Times 3 is negative 3. Plus 1 is negative 2. Times 3 is negative 6, which gives us a 0 remainder, which is perfect. So right now, what do we have? Right now, I know that p of x divided by that x minus 3 gave us a result of, it would, I think, be x to the third plus 2x squared minus x minus 2. So at this stage, I'm going to try to squeeze it in over here. I know that x to the third plus 2x squared minus x minus 2 is equal to x plus 1 times our question mark. So where did the x minus 3 go? Well, I divided it out. I divided both sides by x minus 3, and on the left now I have the x cubed plus 2x squared minus x minus 2, and on the right it canceled out, so I just have my x plus 1 times our question mark. So this writing I did over here I would never do when I'm actually doing this problem on my own, because the next thing I'm going to do is divide both sides by x plus 1. If I divide both sides by x plus 1, then on this side it's going to cancel, and I'll end up with my question mark. So I can do synthetic again, and these coefficients are already listed right here. So don't even bother writing this thing over here. Just use those coefficients, and now we're going to put negative 1 into our box. Draw a line. 1 comes down, times negative 1 is negative 1, plus 2 is 1, times negative 1 is negative 1, and negative 1 are negative 2, times negative 1 is positive 2, gives us another result of 0 there. So now I have my question mark. It's x squared. Remember, these are the coefficients. So 1x squared plus 1x minus 2, which hopefully is what we got with the long division. And it is. X squared plus x minus 2. It's exactly the same thing. So once again, I've shown that our polynomial p of x is equal to x minus 3 times x plus 1 times x squared plus x minus 2. So this is definitely a lot faster, just doing the two synthetics as opposed to the long division. There's also a lot less room for error, because when you're subtracting those x's, man, I just feel like there's so many places that you can go wrong. So are we quite done yet? Well, not quite. So either way that I do it, when I finally want to be able to factor this into its parts. So like before with the 210, we found that now it's equal to 2 times 3 times 35, but 35 we can actually split into 7 and 5. Just like we can split that 35 into 7 and 5, we can split this quadratic into two factors. So maybe you're really good with factoring. We could make an x box. There we go, x box. And in the top we'd have negative 2 times 1, which is negative 2. And then on the bottom we have b, which is just 1. So we need two numbers that multiply to -2 and add to +1. Well, I think 2 and -1 will do the trick there. So we get our two factors, x plus 2 and x minus 1. We could also use quadratic formula here, especially if we couldn't factor it. If we had like complex roots here, we would want to use quadratic formula. So the moral of the story, our whole polynomial, x to the 4th minus x cubed minus 7x squared plus x plus 6 is equal to x minus 3 times x plus 1. Those were the two that were given, and now we found our last two roots, times x plus 2 times x minus 1. So I'm going to make another video that is going to have a lot more examples where we have some roots that are complex. This one was pretty simple just because we had all real roots here. But you want to watch this a couple times before you move on to that. You want to make sure that you're understanding how we are able to get these last factors, where this polynomial came from, the quotient from dividing by x minus 3 and x plus 1, and the way that we solved the problem, that we were able to completely factor this thing out. So we were able to get all four of our factors. Now, there is a method to doing this. So every time that you do these problems, you'll notice that it's going to work out the same way. The first thing you do is find as many zeros from the problem as possible. So in this problem, they told us 3 and -1 are factors. So the first, or excuse me, zeros. So if they tell you that 3 and -1 are zeros, then we can get the first two factors. So you want to write out as many factors as you can. Because if you can find as many zeros as you can start, you already have a couple factors. So with real zeros, one way to do that is if it's given. Another way is by graphing. We had one example much earlier in the first video where we graphed to find all of the zeros. Complex zeros, only way to do that is if they give you one complex zero. So let's say they give you, like, I don't know, 7 plus I is a root. If 7 plus I is a root, then the conjugate zeros theorem says that 7 minus I must also be a root. So then remember, our factors would be x minus 7 plus I and x minus 7 minus I. We just subtract the 0 from each of the x's. So like I said, we're going to have some examples in the next video where we're going to have some that deal with complex numbers because they get a little tricky. You just have to remember to keep everything straight. So the next step is to write out the polynomial with as many factors as you know. So in the example that we had, we started that with x minus 3 times x plus 1. And then we said there's some other question mark here, and we don't know what it is. So that's how I always write it out. As I say, my polynomial right now, I know it's x minus 3, x plus 1, and there's some other number there. I don't know what it is, but I'm going to find it by doing division, and that's the next step. We're going to use division, either long or synthetic, especially if you have linear factors, you can use synthetic division. You can even use synthetic division if you have complex values, and you're going to see that in the examples in the next video, to find that missing piece. And that missing piece is probably going to be a quadratic. Why is it going to be a quadratic? Because we know how to find the zeros of quadratics. We can either factor it, or we can use quadratic formula, which is your last step. So you can use Xbox factoring on that quadratic, or you can use quadratic formula to find those last zeros. And then you're going to be all set, and you'll have all the factors of your polynomial. So that is the big idea for using the fundamental theorem of algebra. I hope this has been a little bit more helpful. Watch it a few times if you're still having issues with it, and see if you can make sense of what we're doing to be able to factor these higher order polynomials. Thanks for watching.